Today we are going to continue our discussion on sintering of ceramics. Earlier we have introduced the subject, we defined what is sintering, what do we expect out of sintering, and few kind of results or the effect of sintering on the material was discussed. We will continue more or less the same discussion and go to other aspects of this particular phenomena. This particular view graph was presented earlier, where we have plotted the grain size against percent theoretical density, because one of the basic effects of sintering is the increase of density. From a porous material we actually proceed towards a dense material, and of course, the idea is to have the theoretical density 100% density, all the pores must be removed, but it is just does not take place just like that. It is also associated with many other effects. One of them, of course, the grain size. The starting particle size is finer, and as we sinter or densify it more and more, the grain size also start increasing. However, it is not a uniform increase. Depending on the situation, there may be 3 different cases which has been presented here. One is, as we discussed earlier, is the pure coarsening of the initial particles. So, there the grain size increases very fast without changing without much change in the theoretical density. So, if initially the finer particle get coarsened by some process, we will discuss how exactly they can do, then the grain size increases quite fast without increasing the theoretical density. The other extreme is on this side, that is the densification initially proceeds without much change of grain size, and then towards the end, very close to the theoretical density, 100% theoretical density, there is a sudden change in grain size. So, this is densification followed by grain growth. So, initially densification takes place, then the grain growth takes place. Here without densification, the grain growth takes place. So, pure coarsening, and here this situation is somewhere in between this, where both coarsening and densification proceeds more or less simultaneously. So, depending on the experimental condition, depending on the starting size of the powders, their properties, their surface properties, and so on, such situations may arise, and we have to understand why it is taking place or why this is happening, and accordingly take some corrective measures wherever necessary. So, these are the 2 extreme cases, and this is somewhere intermediate, and depending on the situation, depending our goal, we can control these properties or control this behavior to a large extent. This is another situation, or if the phenomena can be described in a slightly different way. Here we have plotted once again grain size versus pore size, not the theoretical density which I have plotted earlier, but here it is grain size again plotted on the vertical axis, and the horizontal axis is the pore size, because theoretical density, increase of theoretical density is also actually reduction of the pore size or the pore volume. So, here this is our starting situation or starting condition, where this is the initial configuration, where somewhere this is a pore size here and the grain size there. So, initially when a compact is made, particles are consolidated by some technique what we call the green compact before firing, and that green compact has a green density also. So, depending on that density, the pore size will also there depending on the particle size, and then as we proceed with the sintering, the particles get coalesce with each other and form some grains. So, if the pore size is increasing, then this is a situation where the pore size is increasing and grain size is also increasing, right. From here we are increasing the grain size and the pore size is also increasing, and this is what happens. There is a relationship between the coarsening of the particle. Earlier we have seen when the grain size, we go to the next earlier slide. Yeah, this is coarsening, and that is what happens. This has been plotted in a slightly different way, not in the terms of theoretical density, but pore size. So, when coarsening takes place, this happens. Pore size increases, grain size also increases more or less in a linear fashion, right. Whereas, if there is densification and then grain growth here, then the pore size actually reduces, pore size do not increase. So, pore size, because our purpose is not to increase the pore size, is actually decrease the pore size. So, by sintering our aim is, our objective is to decrease pore size and as a result get densification. And as we decrease more and more the pore size, towards the end there will be a grain growth. Okay. So, from this, this is not a preferred situation. This is not a preferred situation where pore size is also increasing and there is a grain size is also increasing, and which results from the particle coarsening, initial particle coarsening, which is not a very desired situation, whereas more desirable situation is this one, where the pore size is increasing and consequently there is a densification, and then towards the end there is a grain growth and the pore size becomes finer and finer. Okay. So, you have a correlation between pore size and grain size as well as grain size and theoretical density, what we have discussed earlier. So, our objective is to avoid this coarsening of the particles before it gets actually sintered. Well, what is really happening when you are sintering a product or sintering a ceramic material? The main thing what is happening is a mass transport. Okay. Sintering is the result of a mass transport in an atomistic level. So, the mass transport and sintering has a very direct correlation, and mass transport, or in other words the movement of the atomic species from one site to the another, is the primary mechanism by which the sintering occurs. So, sintering means actually there is a mass transport at the atomistic level and at a very micro level. Okay. So, while solid state diffusion is the most important mechanism of mass transport, well, there are different mechanisms of mass transport, or we might have discussed in other courses. In this course, we have not discussed in detail what are the mechanisms of mass transport. I am sure diffusion is known to everybody. So, the solid state diffusion is the most important mechanism of mass transport. However, there are other mechanisms also. It is a vapor phase transport can also take place. That means, the material is getting transported from one site to another through a vapor phase. Okay. Diffusion, of course, as we mentioned, diffusion is one of the very most common and important mechanism mass transport, where the atom by atom movement is taking place in the structure, in the crystallographic structure or the assembly of atoms. The other possibility is the vapor phase, which means from the surface the materials gets evaporated to the vapor phase and then gets deposited somewhere. So, it may be within that material or it may be outside the material. So, it is kind of an evaporation, right, evaporation and condensation, one can say. The condensation can take place at some other site of the same material or same piece of substance, or the condensation can take place at some other place on other substrates, which is actually the phenomena takes place in thin film deposition by evaporation or physical vapor deposition. There is another technique or mechanism by which mass transport can also take place, the capillary flow of liquid. In case of a liquid, because of the surface tension force and the capillary action, the liquid can move from one place to the other, and that also is a form of mass transport. So, capillary flow of liquid is also an important particularly for liquid phase sintering. Earlier we have discussed the solid state sintering and the liquid phase sintering. So, if you in solid state sintering, these are the two mechanisms which are more important, diffusion mechanism. Of course, we will see later on that the diffusion mechanism also have different variants, different types of diffusion and different paths of diffusions are possible. In addition to diffusion, in the solid state sintering or solid state mass transport, you have a evaporation and condensation, whereas in a liquid phase the liquids moves normally by a capillary flow technique or a viscous flow technique or viscous flow mechanism. So, we will discuss those things also. So, what this particular slide means or conveys that there is a strong or a very important correlation between sintering and mass transport. In fact, sintering is the result of mass transport at the atomistic level. Now, whenever there is a mass transport in the atomistic level, there must be a driving force. Why the mass should or the material must move from one place to the another place or another site. There has to be certain driving force. We have earlier discussed that sintering takes place because of there is a global driving force, that is because of the change of surface energy to the surface area changes, and therefore, the additional energy due to the surface energy decreases, and therefore, there is a driving force, and the surface energy is the major change of surface energy is the major driving force in the overall or global level. And also we have just now discussed that surface energy change is actually realized by mass transport phenomena. And so, there will be a mass transport, there will be again another driving force at the atomistic level, and that is what we are called local driving force. While the global driving force, as mentioned earlier, is the lowering of the free energy through elimination of the excess surface energy, there must be a local driving force for the mass transport to occur at the local level. As the preliminary driving force for diffusion is the concentration gradient, and that for the primary, as the primary driving force for the diffusion is the concentration gradient, and that of the vapor phase transport is the gradient of the vapor pressure. It is necessary to understand how these gradients are set up at the local level. So, because diffusion is basically requires a concentration gradient, right. So, that is the Fick's first and second law says that until and unless there is a concentration gradient, diffusion cannot take place, and we are telling that the diffusion is one of the primary causes or mechanisms by which sintering takes place. So, there must be a concentration gradient set up at the local level or at the atomistic level, or if you are talking about vapor phase transport, then there must be a difference in the vapor pressure at different sites, so that the vapors can move from one point to the other, or the material can move from one point to the other. So, we have to understand how these concentration gradients or vapor pressure gradients are getting realized at the local level, at the atomistic level. In this context, curvature of the particle surface play the most important or the crucial role in realizing these gradients, okay. Because what by sintering, what we mean, we have the way we have defined sintering is the agglomeration or the agglomeration of certain particles, okay, which when heated or provided the activation energy, by heating it to higher temperature, they just get coalesced with each other and forms a strong bond. So, there is no other we are not creating any concentration gradient by from outside. Okay. So, there is only some particles, and just the conglomeration of these particles generates some amount of certain type of concentration gradient or the vapor pressure gradient. So, the reason is the curvature itself, the particles having different curvatures, different sizes of the particles will have a different curvatures, and at different sites they have a different nature of curvature, and it appears that this curvature itself plays the most important or most crucial role in realizing these gradients. So, that is what we have to understand, how this curvature becomes so important in setting up these kind of vapor pressure gradient or even concentration gradients. So, that will be our discussion in the next few minutes. So, the local driving force and curvature of the solid surface, that is what we like to discuss or understand. Point defects such as vacancies play the most pivotal role in diffusion mechanism of mass transport. Diffusion takes place, or diffusion arises or takes place in a solid primarily by point defects, by the presence of point defects, and vacancy is one of the most important point defects which causes material transport or mass transport in a material. So, there is a vacancy mechanism of diffusion. So, if the diffusion has to take place, can we expect a vacancy gradient? Okay. So, that is what is our objective now. In addition to the dependence of its concentration on the temperature and impurity content, it is also dependent on the curvature of the solid surfaces at the local level. We know from our discussion of point defects, the point defects are created at a higher temperature, because we provide at higher temperature a activation energy is provided for the creation of these defects. These defects are thermodynamic species, and creation of defects lowers the free energy of the system. Therefore, there is a temperature dependence and an exponential temperature dependence. So, defects are certainly created by increasing the temperature. That is one way of introducing some defects. In addition, if you add impurities to that, we have also seen in earlier lectures that by adding certain impurities of different valency, one can also create vacancies, okay, because of the charge neutrality requirement. So, these are the two known parameters by which one can generate vacancies. However, in this case, in currently what we will look at, the change of curvature also sets up a vacancy concentration. So, the concentration of the vacancy is not same throughout the surface. If there is a change in curvature of the surface, the concentration also changes, particularly of the vacancies. And therefore, it is necessary to understand the variation of the vacancy concentration and also the vapor pressure concentration. These are the two terms we are basically looking at. One is the vacancy concentration, how it changes with the curvature, and the other is the vapor pressure of the material. Is it a function of curvature? That also is our interest. Now, if you want to understand this, we have to look at something slightly different from a analogous situation, where let us say this is a what we call the Gibbs Thompson equation. It actually relates the calculation of work done to increase the size of the gas bubble. In fact, it is basically how the gas bubbles are created. For example, soap bubbles, it grows under certain situation, it collapses under certain situation. So, from that one can find out what will be the energy required, and is there any difference between the energies of the two different surfaces having two different radius of curvature. So, that is what we will see here. The work, this is a gas bubble, which is, this is the surface of the gas bubble, a film, basically a film which is trying to grow because there is a pressure. Okay. So, there is a pressure generated. Because of the pressure generated, it is giving a isostatic or isostatic pressure in all directions, and the bubble is growing. And this work, this pressure is creating or making some work done. So, the work of expansion of the bubble is actually equal to the increase in the surface energy. So, the work done is against the surface tension forces. Okay. So, that must be equal, the energy, surface energy, and the work done must be equated. So, in this form if one can do, the delta P is the difference in pressure, and dV is the change in volume, and gamma is the surface energy, and dA is the change in area. So, this is per unit area. So, the change in area. So, this is the work done by the surface energy term, and this is the work done by the pressure difference. So, that must be be equated. For a sphere of radius r0, if this is a sphere of radius r0, dA dV equal to, one can calculate from geometry, that 8 pi r by 4 pi r r0 square, that should be r0, that should be r0, not r0 square. So, it will become 2 by r0, 2 by r0. So, delta P will be equal to 2 gamma by r0. Okay. So, that is how from this equation. Okay. So, that is on relationship between the pressure required to increase or put in equilibrium, at what size or what r0 will be, that will be determined by the surface energy term as well as the pressure term. To continue that, the Gibbs free energy change may be written as, this is a very simple equation, everybody knows, dg is equal to V dP S dt. S is the entropy term, T is the temperature, this is the pressure and this is the volume. So, the change in Gibbs free energy is given by this. For an isothermal situation, dt equal to 0. So, dg will be equal to V dP, and by integration one can find that delta G is actually V delta P. For one molecule, 1 mole of gas, and substituting the value of delta P, one gets delta mu. Delta mu is the change in chemical potential. Mu is here the chemical potential. So, one can get 2 gamma Vm by Na Avogadro number into R0 equal to 2 gamma Va by R0, where Vm is the molar volume, Vm is the molar volume of 1 mole of gas, 1 mole of material, and Va is the atomic volume. Okay. So, that it is given by Vm by the Avogadro number, Vm by Vn, this becomes actually Va, that is what has been substituted here. So, the delta mu term, the change of chemical potential is actually related to the surface energy and of course, the atomic volume and the size of the sphere, of that gas bubble. So, based on this Gibbs-Thompson equation which has been just derived, it can be shown that the chemical potential difference per formula unit, that is what has been done earlier, the delta mu, that is the chemical potential difference, which is the difference between a flat and a curved surface, may be expressed as delta mu between a curved surface and a flat surface. Okay. So, this is mu c is that of a potential of a curved surface and mu f is of a flat surface, and that gives the difference is delta mu equal to gamma S b now. Okay. S b is solid to vapor, the solid to vapor surface energy, and then V mx and RC. RC is the radius of curvature, not the radius of the sphere, but it is termed as radius of curvature, and there is of course a relationship between the radius of the sphere and that of the RC. So, RC equal to 2 by R0, that is again from the geometry one can find that, and so there is a difference in potential between the curved surface and the flat surface, and that can be expressed in terms of the surface energy between the volume and the between solid and vapor in this case. So, we are not talking about the gas bubble here, we are actually talking about two surfaces of the solid, two surfaces of a solid, where one is a curved surface, it may be concave, it may be convex, and another is a flat surface, and that depends on the surface energy term between that solid and the vapor and the adjoining vapor. So, that we have introduced earlier also, the gamma S b and V mx. Here we are talking about a material called of the form mx, m is the metal, x is another anion. So, it may be an oxide, so it may be an MO also. So, whatever is the compound, it is not an element now, we are talking about a compound of the form mx, and this Vx is the volume of the formula unit, okay, one formula unit whatever the volume is, and then Rc is the curvature of the solid surface. So, from that Gibbs Thompson equation, we find out that there is a difference in potential, chemical potential between these two surfaces. So, this is the relationship between the radius of curvature and the radius of the sphere. Now, what are the different parameters which depend on the curvature of the solid surface? These are the two most important parameters which depend on them. The potential difference between flat and curved surfaces lead to difference between these two parameters. One is the vapor pressure over these surfaces and the vacancy concentration just below these surfaces. Okay. So, if you have a surface, a curved surface, either a convex or concave, that will have a different vapor pressure than a flat surface, which can be taken as the reference. Okay. So, between a flat surface and the curved surface there is a chemical potential difference, and that also leads to a vapor pressure difference. And the vacancy concentration just below these surfaces also, because on the surface there is we cannot consider a vacancy to be on the surface. Vacancies are within the solid, a vacant space. In fact, coming to the surface it gets annihilated. So, the vacancies just below the surface also changes, its concentration changes depending on whether it is on the flat surface or a curved surface. So, these are the two most important observations from the earlier consideration, that is the Gibbs Thompson equation and consequent the chemical potential. So, because there is a chemical potential difference between the curved and the flat surface, consequently there will be vapor pressure difference and also there will be vacancy difference, vacancy concentration difference. Now, we can do some calculations. Of course, these are not a very detailed calculations, we are not able to present here, but some they are not completely empirical, but they have some mathematical basis, but we will see only the final results in most of the cases. So, the curvature dependent vapor pressure, we have seen that there is a pressure difference, but how much is the difference and what is its consequences. This is delta mu again, and that can be related to either concentration difference or the partial pressure difference. Here it is, you can call it partial pressure or vapor pressure. So, delta mu actually is Kt, K is the Boltzmann constant, T is the temperature, and ln Pc by Pf. In this case, the two partial pressures, one is on the curved surface, another is on the flat surface, that is your reference. So, that is delta mu, and then this gives to ln Pc by Pf equal to Rc. Now, once in delta mu has been expressed earlier, here delta mu is here. Okay. From this also we get that expression Rc equal to Vmx gamma Sv by Kt. Gamma Sv is again the surface energy, solid to vapor surface energy, and then this is also the volume of the one molecular unit, one formula unit of Mx, and then Rc is the radius of curvature, and Kt as usual the Boltzmann constant and the temperature. So, from this you can get delta P by Pf, okay, delta P by Pf, which is nothing but this Pc minus Pf by Pf. Okay, Pc minus Pf is the delta P, and then this become Rc Vmx gamma Sv kT, okay, the same thing. Now, this has come because this has been expressed in this fashion because the difference is very small, and so this can be approximated as this. Okay. Then from this equation P c becomes equal to P f 1 plus R c this expression. Okay. So, there is a relationship now that the partial pressure or the vapor pressure on the curved surface over the curved surface is equal to the vapor pressure on the flat surface multiplied by 1 plus this term. Of course, the R c is there, R c is the radius of curvature. So, the radius of curvature comes into this expression, and this is the relationship between partial pressure of the curved surface and the partial pressure of the flat surface. Okay. So, if this becomes our equation or relating these two partial pressures or the vapor pressures, the same thing has been written here. Then we can have three different conditions quite obviously. For a flat surface R c equal to 0 because the r equal to infinity. So, R c becomes 1 by infinity equal to 0, and that leads to, this is not greater than, this leads to P c equal to P f. So, these two terms will be equal, so which is obvious. On a flat surface P c will be equal to P f anyway. But the more important results are here. For a concave surface T c is negative. Okay. So, if this is negative, this becomes total quantity becomes negative, and then this quantity becomes less than 1. Okay. So, this becomes less than 1, and therefore, P c, the curved surface or the vapor pressure on the curved surface over the curved surface is less than that of the flat surface. Okay. So, P c is less than P f. On the other hand, for a convex surface R c is positive, okay. R c is positive. So, that leads to P c is greater than P f. So, on a convex surface the vapor pressure becomes larger than that on the flat surface, whereas on a concave surface this is smaller or lower than that of the flat surface. So, these are the two most important findings out of this analysis what we have presented there. So, convex surface has a higher, that is the same thing is written here, convex surface has a higher vapor pressure than that of the flat surface, and the concave surface will have a lower vapor pressure than that of the flat surface. So, without changing the temperature, without changing the concentration or the impurity content or the composition of the material, just by changing the surface as a curvature of the particle which we are trying to put together. So, those particles will have a different vapor pressure at different points. If it is of course a spherical surface, it will be uniform everywhere, but we will see when an agglomerate or a conglomeration of particles are made, all the surfaces are not really of similar curvature. They have a different curvatures at different points and different sites, and then somewhere it is a positive, somewhere it is negative, and that actually makes the difference, and that creates so called the local driving force which we are talking about. The local driving force, that is either the concentration difference of the vacancy, or in this particular case here we are talking about the vapor pressure difference. So, the vapor pressures are automatically changes depending on the curvature. So, it is irrespective of temperature, irrespective of any composition. This is what we have already discussed, just a pictorial representation. The curvature dependent vapor pressure, we have a flat surface there. This is a convex surface, this is a convex surface, and this is a flat surface, and this is a concave surface. Okay. So, these are the same composition kept at same temperature, but just because their radius of curvatures are different, the vapor pressure will be different. So, the P convex, the vapor pressure on this surface, that means if you measure the vapor pressure just above this surface at any temperature, you will find some value, and that is more than what is the vapor pressure here on a flat surface, just above the flat surface. Incidentally, you must know that whenever a material is kept in anywhere in any environment, there is always an equilibrium. So, there will be always some vapor of that material, solid vapor will try to equilibrate with the gas phase, whatever the gas phase is. Okay. Of course, this equilibrium becomes more, or the kinetically it becomes faster when there is a high temperature and the evaporation rate is fast. If the evaporation rate is not fast, of course, thermodynamically it has to be in equilibrium, but the kinetically it may be a very sluggish or slow process. Finally, if you have a concave surface like this, that also have some vapor pressure here of the same material. So, some vapors of the same material will always be there depending on the temperature, of course. If the temperature is low, then the gradient will be high, because the evaporation rate will be very low. If the temperature is high, the evaporation rate will be high, and there will be always an equilibrium. Okay. So, that vapor pressure, the concave vapor pressure corresponding to the concave surface, is still lower than this. So, this is highest, this is intermediate, and this is the lowest. Okay. So, that is the important observation or important conclusion to our findings of whatever mathematical analysis we have done so far. Next is we are talking about two terms, two driving forces. One was the vapor pressure for vapor phase transport, other was the solid state transport. Of course, solid state is within the solid itself without involving the vapor phase. This is the curvature dependent vacancy concentration. We can also write some equations for that, but this is a different equation. This is just a temperature dependence of any vacancy concentration. That was we discussed earlier when we were talking about the point defects, the creation of point defects, either the vacancies, interstitials, Frankel defect, or the Schottky defects, right. So, for creation of any such defect, we need a activation energy, and here this is the enthalpy. The enthalpy change delta V, delta H V is the enthalpy of formation of a defect. So, the enthalpy change is delta H V, and that gives us the temperature dependent exponential temperature dependence. So, C 0 is a constant T exponential term, exponential minus delta H by k T, this is so called Arrhenius equation, the well known Arrhenius type of equation. Since the energies at the flat and curved surfaces are different, that we have seen that the potentials are different by delta mu. So, since they are different, the enthalpies required to create vacancies at the flat and the curved surfaces are also going to be different. Okay. So, the energies at different surfaces, we have seen that energies are different, and that energy also leads to the vapor pressure difference. For the same reason, since the energies are different at different surfaces or different types of surfaces, the vacancy concentration just beneath it, because you need certain energy to create these vacancies. So, if the host material has different energies, naturally the available energies will be different, and or you have to work against different energies. Therefore, the concentrations of the vacancy just below that surface will also be different. Okay. This is in addition to the temperature effect. So, this can be expressed in CV, the vacancy concentration at a curved surface is equal to C0 exponential minus. So, that was general term, temperature dependent term, let us say on a flat surface, and that plus the delta mu. The delta mu is the chemical potential difference which we have discussed earlier. So, if that is added to that, that will be the total activation energy needed for creation of the particular vacancy, and this can be simplified as C1, another pre-exponential term with delta mu again can be replaced by RC mx Vmx gamma is V and then kT. So, these are earlier we have seen. So, if as RC Vmx and gamma is V, this term is much less than kT, this the numerator is much less than the denominator here. So, the expression may be modified as this exponential term can be changed to this kind of a expression CV curve, that means at a curved surface, and C0 actually we will see although a pre-exponential term, but ultimately you will find that C0 is actually the flat surface. So, this is simplified, exponential term is simplified into linear fashion, a linear expression, and then for a flat surface RC, that RC radius of curvature here, which comes from the mu delta mu term, RC equal to 0. If RC equal to 0, this whole term becomes 0. So, CV at a curved surface, that is the vacancy concentration over a curved or below a curved surface, almost equal to C0, which is nothing but the vacancy concentration at the flat surface, because for the flat surface we have taken RC equal to 0. Okay. So, this C0 becomes actually a flat surface vacancy concentration, and that is by definition RC equal to 0. Now, in the similar fashion what we have seen in case of vapor pressure, the concentration of the vacancy over a curved surface or below a curved, or not over, it is a below a curved surface is almost equal to CV flat C0. C0 has been replaced by this, and 1 minus the same thing, same expression RC Vmx gamma is V by kT. Now, if this becomes the final expression for the concentration on a curved surface with respect to the flat surface, then we will have two conditions. We will have two conditions. One is RC is positive, as you have seen in the case of the vapor pressure. If RC is positive, then the concentration of the vacancy on the convex surface, this is true for a convex surface, is less than the concentration on a flat surface. Okay. So, if this is positive, this becomes a negative term, and that is once it is deducted from 1, it is actually less than 1. So, the concentration on the convex surface is less than that of the flat surface. Similarly, in a concave surface RC is negative. So, this becomes positive, then negative is positive. So, CV the concentration on the concave surface becomes more than that of the flat surface. So, that is another very important observation or another findings out of these analysis, mathematical analysis what we have little done here. So, ultimately our conclusions or the findings are that the concentration below the convex surface is less than that of the flat surface, and the concentration, vacancy concentration below a concave surface is more than that of the flat surface, and that is very significant and important for our purpose. So, finally, this is our conclusion summary of the curvature dependent properties. This is for the vapor pressure, we have seen it earlier, and this is for the concentration of this is for the vacancy concentration, right. This is for the vacancy concentration, and you can see the two things are in a reverse order. Here the convex is more than the flat, and the flat is also more than the concave. Here is the reverse. The convex vacancy concentration on the convex is less than the flat and is still less than the concave. So, the here is the concave is the highest, whereas here convex is the highest. So, they are in two different way or in the order is difference. Okay. This is one kind of order, this is another kind of order, and we will see later on how all these differences actually lead to mass transport and then to the sintering process, right. Before that, let us have another consideration. So, far as sintering is concerned, sintering is a time dependent phenomena. It is also dependent on temperature, it is also dependent on time. So, both time and temperature are two very important parameters which controls the sintering process, and also we know that by sintering actually there is a densification from a porous material, a more dense material or a more sound material is prepared or formed by sintering. So, the whole process of sintering has been subdivided into three different stages. The complete process of sintering can be divided into three distinct stages depending on the geometrical changes, particularly in terms of pore shape and size that the sample undergoes during the sintering process. Okay. So, basically during the sintering sample undergoes some geometrical changes, particularly in terms of pores size, pore volume and distribution and so on, and also the mechanical strength increases, densification changes, increases and so on. So, whole process can be subdivided into three different stages depending on what extent of densification has taken place, how much time we have allowed and so on. So, the first is what is called initial stage of sintering. Here the contact area, because we are talking again a conglomeration of some particles, so fine particles. So, there will be some contact area between the particles. It may be very small to start with. If we take a spherical or uniform size spherical particles, the contact area theoretically it will be a kind of point contact, but actually there will be some kind of finite contact area between the particles. So, the contact area increases by neck growth. We will see what is really neck growth. It is actually at the area of the contact, we call it a neck. Neck is formed between the two particles, and this neck growth initially it is obviously the area of the neck growth. Initially it should be 0 theoretically, and then as the sintering proceeds this neck area increases. So, in the initial sintering stage, that by definition it has been empirically defined in this manner, that it increases from 0 to 0.2, 1 being the final figure. So, 0 to 0.2, that means about 20% growth has taken place so far as the area of the contact area is concerned between the particles, between all the particles, and the relative density is up to a maximum of 65% of the theoretical density. So, relative density is about 65% and then neck area has grown up to about 20%. So, that is the initial stage, we define it as an initial stage of sintering, and then we have an intermediate stage. This is the longest stage of sintering in time scale, during which the relative density increases from around 65, from this 65 to around 90%, and the pore remains continuous. Pore to start with is a continuous phase, because you have only contacts, point contacts. So, the pores to start with are continuous, and solids are also continuous. So, it is a interpenetrating two different phases, the solid phase and the pore phase or the gaseous phase, and 65 to 90% and the pore still remains continuous. Okay. So, that is the longest sintering stage in terms of time. And the third stage is called the final stage of sintering. It begins when the continuous pore gets separated into a large number of isolated pores. Towards the end, when the pore volume decreases quite significantly, because 90% densification has already taken place, starting from 50 to 60%, we have gone to about more than 90%. So, only 10% of the pore are still remaining, and they need not be, most of the time they are not continuous. So, they becomes isolated pores which may be lenticular in shape if they are along the grain boundaries, or nearly spherical if they are away from the grain boundaries or within the grains. So, they get isolated, the continuous phase, the pore is no longer a continuous phase, solid remains continuous, but the pore is no longer continuous, they become isolated, and their shapes of individual pores depends on where exactly they are located. They may be located at the grain boundaries, at the contact area between the two grains or the two particles, or they may come within the grains, and they are remaining become isolated. So, whichever is within the grains, they tend to become spherical, whereas which were within at the contact area of the grains or between the two grains or the grain boundaries, they will be little elongated in nature. So, these are the three different stages depending on the extent of sintering, extent of time spent for the sintering operation, and the growth of the grains as well as the reduction in the pore volume. However, the final conclusion is like this: the sintering kinetics are different during the different stages of sintering. The kinetics are different. Different atomic mechanisms of mass transport may be operative at different stage of sintering. So, it is not necessarily that the same mass transport mechanism will be operative, and their kinetics may also be different. So, the overall the sintering is a very complex phenomena, and many different processes do take place simultaneously. So, the mathematical analysis is certainly complex, and we will take it up to further things how exactly everything happens in a slight more details in the next class, and we complete or we end this class here as the time is up. So, thank you for your attention.